Hey guys, welcome to lesson 25, and this is going to be our last lesson for this class. All right, in this lesson, we are shifting gears completely and talking about systems of equations. All equations of the form ax plus by equals c are straight lines with graphs. Two such equations are called systems of linear equations or a linear system. A solution to the system of equation in two variables is an ordered pair that satisfies both equations in the system. All right, we just talked about how they have a graph. So where they intersect is your solution. Okay, so we are dealing with straight lines. We must consider three possible solutions: one, none, or infinitely many. All right, so if they cross, you get one solution. If they're parallel, you don't have anything. You have no solution. And if they end up being the same line, because they're equivalent, then we have infinitely many solutions. And so your solution, your one solution, is going to be an ordered pair. All right, no solution means I'm going to write it like that, and we also can say that this is inconsistent. So if we have infinitely many solutions, we're going to write the rule for the solution to follow, and I'll tell you exactly what that means in a little bit. All right, so using graphing to find the solutions of a system of linear equations is a very practical way to find one of the above solutions. However, this is only one of three methods for solving systems of linear equations. All right, so graphing is obvious, but there are two methods, substitution and elimination, that we can use algebraically that are particular, and these are particularly helpful when I don't get straight answers like whole numbers. All right, so for number one, we're going to do substitution. All right, so what does that mean? Well, let's see. The second one, it says x is already by itself, so I'm going to take this and I'm going to say x equals 2y plus 1. And then I'm going to take that, now that I know what x is, I'm going to plug it into the second one, or the first one rather, and say 4 times x, and x is 2y plus 1 minus 3y equals 14. All right, this allows me to get an equation with one variable, which I can solve for. So this would be 8y plus 4 minus 3y equals 14. All right, that's going to be 5y plus 4 equals 14. 5y equals 10, y equals 2. All right, now that I know what y is 2, I'll plug it into this x here. So x equals 2 times 2 plus 1. So x equals 5. So I write my answer as an ordered pair, 5, 2. So these two equations will intersect at that point, 5, 2. All right, elimination. All right, I would really like it if, so the whole point of elimination is I'm going to add my columns and get rid of a variable. All right, as of right now, the only thing that makes sense is to get rid of the y's, but in order to do that, I need to multiply each of these in order for, the signs are different, but the numbers are not. So I need to make the numbers the same. So on the top, I'm going to multiply by 2, and on the bottom, I'll multiply by 3, so that I get 6 y's right there. And so here's what's going to happen. When I multiply the top one by 2, I get 4x plus 6y equals negative 2. And on the bottom, I get 9x minus 6y equals 54. But what happens is, now my 6y's get to fall out. And then I just add my columns. I got 13x equals 52. And then 13 divided by 52 is 4. So x equals 4. So at this point, we didn't do any manipulation like we did on number 1. So just pick your favorite equation and plug 4 into it. So this would be 2 times 4 plus 3y equals negative 1. So you got 8 plus 3y equals negative 1. So 3y equals negative 9. Y equals negative 3. So 4, negative 3 is my answer here. These two equations will intersect on a graph at 4, negative 3. All right, so that's substitution and elimination. Okay, well, whether you use substitution or elimination is really up to your preference. And a lot of times it's determined, or at least for me, it's determined by how the problem is set up. Like for number 1, it was really straightforward. I could have done elimination, but x was already by itself. and I was going to have to multiply anyway to get elimination, like there was nothing there to begin with. So substitution made sense. Or like on number 2, like the signs were already different, so it made sense to go ahead and get rid of the y's by elimination. So it's really problem specific whether or not you decide. You can use either one on any problem, but I typically decide which one to use based on how the problem is set up to begin with. All right, on number 3, let's see, I got 7x and 3y. I could get rid of the x's or the y's. The signs are different, and so if I just multiply this top one by 2, let's see what happens. All right, that gives me 14x plus 6y equals negative 10 over negative 14x minus 6y equals negative 10. So when you add this, your x's and y's fall out. You're left with 0 equals negative 20, which is a false statement. All right, so this is no solution. And you can spell it out, or you can say 0 with the line through it. And again, we called this earlier, if it's no solution, that means it's inconsistent. Okay. Now, number 4. Let's see. I could pick my x's have different signs, my y's have different signs, so I just need to pick one. All right, so let's take the bottom and multiply by 3. So let's say negative 9x plus 3y equals negative 24. The bottom is going to be a positive 9x minus 3y equals positive 24. And when I add, everything is going to fall out. All right, so I get 0 equals 0, which means these are the same line. So what do I do? Well, the second equation, y is by itself. So what if I solve this one for y? And so that would be negative y equals 3x, or negative 3x plus 8. Y equals 3x minus 8. So since I solve for y, x is going to be my the thing that I plug in. So whatever x is, I plug that into this rule. And so I said earlier that whenever it's infinitely many, which is what this is, whenever it's infinitely many, like this one is, then you have to write a rule for whichever variable you don't solve for. So I solve for y, so that's my rule. So no matter what I plug in, it's always going to work because it's the same line. So if I plug in x, I get my y by plugging it into the rule, 3x minus 8. Okay, now, a lot of times, once you get the basics of system equations, they really start to kick into gear once you get to application problems. And so in this box, you have a list of steps of how to use them. But let's go ahead and get started with number 5. All right, we're finding the break-even point. So you have cost, which is the money you're spending. Revenue is the money coming in when you sell stuff. Your profit is when you're no longer hemorrhaging money, but you are actually making money. All right, so you got money coming in, you got costs going out. All right, when those are equal, that means you have broken even. You're no longer losing money, but you're also not making money. You have to keep selling to make money at that point. So technology is now promising to bring light, fast, and beautiful wheelchairs to the millions of people with disabilities. A company is planning to manufacture these radically different wheelchairs. Fixed cost will be $500,000, and it will cost $400 to produce each wheelchair. All right, well, if you look at this problem, the cost function right here, it says fixed cost plus cost to produce. All right, so that's fixed cost and cost to produce. All right, so that C function is going to be 400x plus 500,000. Okay, and then it says each wheelchair will be sold for $600. So that is going to be my revenue function. So R of x equals 600x. Okay, Now, in order to, like I said before, you make a profit when the revenue is bigger than the cost, but you break even when they're equal. Okay, so if it's asking for break-even point, then I'm going to set these two equations equal to each other. And this is a system of equations. So you get 600x equals 400x plus 500,000. All right, subtract the 400, you get 200x equals 500,000. All right, x equals, you divide by 200, and you're going to find that it's going to give you 2,500 as an answer. X equals 2,500. All right, it says determine the break-even point and describe what it means. All right, so this is the x for it. All right, with any system of equations, you got to find the x and the y. So I'm going to plug this in to the revenue, and so that's going to be 600 times 2,500, and that's going to spit out 1.5 million. Okay, which means my answer is 2,500, 1.5 million. All right, they ask you to describe what this means, and that means the company will break even when they sell 2,500 units, and the price of those units is going to come out to it's going to come out to $1.5 million. All right, we got one more problem. All right, so a chemist is working on a flu vaccine and needs to mix a 10% solution of sodium iodide with a 60% solution of sodium iodide to obtain 50 milliliters of a 30% solution. How many milliliters of the 10% solution and 60% solution should be mixed? Okay, so if I let my 10% solution be X, my 60% solution be Y, and I need 50 milliliters of the 30%. I'm going to multiply these together, and that's going to give me, and I'm going to write my percentages as decimals. So it's going to give me 0.10 X and 0.60 Y, and then 0.30 times 50 is going to give me 15. All right, so if I add these columns together, those are my systems of equations. So I got x plus y equals 50 for one of them, and then I got 0.10 or 0.1x. You can say 0.10 or you can say 0.1. It's the same thing. 0.1x plus 0.6y. Again, you don't have to include the 0. Equals 15. Okay, so you could do substitution or elimination. I'm going to use substitution. All right, so I'm going to solve for x. So that means x equals 50 minus y. All right, so I'm going to take that and plug it into the other one. So that means I got 0.1 times 50 minus y plus 0.6. It'd be consistent. So it'd be 0.6 y equals 15. All right, so if I do that, that's going to be 5 minus 0.1y plus 0.6y equals 15. Okay, well, this is going to be 0.5y equals 10, y equals 20. And since I know what y equals, I can find x. X equals 50 minus 20, so x equals 30. All right, so in short, I'm going to need 30 milliliters of the 10%, and I'm going to need 20 milliliters of the 60%, and that's going to produce, if I multiply these together, that's going to produce 3 milliliters of sodium iodide solution, and that will give me 12 of that. Okay, so how many milliliters of the 10% and the 60%? 3 and 12. That's what I got. All right, guys, that's the end of this lesson. That's the end of this class. Reach out if you have any questions, and I will see you later.